principal component. Let's understand how to find the first principal component. The first principal component is the direction of maximum variance and is obtained by solving the eigenvectors. Principal components are new variables constructed as linear combinations or mixtures of the initial variables. These combinations are done in such a way that the new variables are uncorrelated and most of the information within the initial variables is squeezed or compressed into the first component. You need to multiply your data points with each eigenvector, representing the selected components to project them onto the new space. First principal component is mathematically denoted as A1 x1 plus A2 x2 plus A3 x3 plus ellipsis plus AK xk, where constraint A1 squared plus A2 squared plus ellipsis plus AK squared equals 1. Eigendecomposition is used to solve the above equation. Eigendecomposition or spectral decomposition is the factorization of a matrix into a canonical form, where the matrix is represented in terms of its eigenvectors and eigenvalues. So, let's understand the results of eigendecomposition. Solving eigenvectors results in eigenvalues. Suppose you have values of constraints from A1 to AK. From an eigenvector V1 based on eigenvalues, one eigenvector corresponds to one principal component. This means for each principal component, you should have a separate eigenvector. Principal component is derived by multiplying the original data matrix with the eigenvector, that in return is V1 ratio F1 equals A1 x1 plus A2 x2 plus ellipsis plus AK. Eigenvalue is calculated from the variance of F1, that is, E equals variance of F1. The eigenvectors of the covariance matrix are actually the directions of the axes where there is the most variance and that we call principal components. Eigenvalues are the coefficients attached to eigenvectors that give the amount of variance carried in each principal component. Eigenvalues and PCA. Eigenvalues are the variances of principal components arranged in descending order. Suppose you have the data matrix F1, F2, F3, so on till Fk. PCA tries to put maximum possible information in the first component, then maximum remaining information in the second, and so on. So, the first principal component will be greater than the second, and second principal component will be greater than third, and so on, which also means that the first eigenvalue will be greater than second, and second value will be greater than third, and so on. Let's summarize the PCA process now. Standardize the data if required. PCA requires that the input variables have similar scales of measurement, since you are trying to capture the total variance in the set of variables. Build a correlation matrix. The correlation matrix summarizes how your variables all relate to one another. Obtain the eigenvectors and eigenvalues from the covariance matrix. You break the above matrix down into two separate components, direction and magnitude. Eigenvectors represent directions, while eigenvalues represent the magnitude or importance. Sort eigenvalues in descending order and choose the eigenvectors that correspond to the largest eigenvalues. Bigger eigenvalues correlate with more important directions. When there is more variability in a particular direction, it is indicative of something important you want to detect. Construct the projection matrix from the selected eigenvectors. Eigenvectors are associated with an eigenvalue, which can be interpreted as the length or magnitude of the corresponding eigenvector. The reduction of the dataset via PCA onto a smaller dimensional subspace by dropping the less informative eigenpairs is reasonable if some eigenvalues have a significantly larger magnitude than others. Transform the original dataset to obtain a KK-dimensional feature subspace by identifying which directions are most important. You compress or project your data into a smaller space by dropping the directions that are the least important and therefore reduce the dimensionality of your feature space. Demo feature reduction. Problem statement. The dataset